In this section of chapter 10, I would like to discuss about barometer, manometer, gas laws, and ideal gas equation. Unlike liquids and solids, gases expand to fill their containers. They are highly compressible and have extremely low densities. Pressure is defined as force per unit area. So keep that in mind before we discuss the unit that we, the chemists, often use. The pressure expression is given by H times density times acceleration due to gravity. For the same liquid, pressure is proportional to the height. And so often in chemistry, we use height unit to represent pressure, right? Rather than actual pressure unit, which is given by height times density times acceleration due to gravity. Barometer is the device for atmospheric pressure measurement, and manometer is the device for confined gas pressures. If I have a sample of gas in a container, if I want to know what kind of pressure I have, I'm going to use manometer. Now, on the left, the units of pressure are given: 760 millimeter torr, or 760 millimeter height of mercury. Often we hear about Pascal, but we don't use that unit. Sometimes in some books you'd also see unit as bar. Bar is about 1 atmosphere and 10 to the power 5 Pascal. On the right hand side, you're looking at a manometer, and let's see whether we can answer this question. Atmospheric pressure or outside pressure is given as 740 millimeter of mercury. Now, a confined gas is connected to it, and you find that two sides of this tube has the same height of mercury. The question is, what will be the pressure of the gas? Now, if pressure of the gas, question is pressure of the gas greater than outside pressure? Or is it lower than outside pressure? Or is it equal to outside pressure? Just by looking at it, you know it must be equal, because that's why two levels are the same. So think about a seesaw. I often give this analogy. This is a seesaw. This end and this end, when they have same pressure, it should be pretty much horizontal. Seesaw would be horizontal. And that's what you see here. Let me draw a dotted line. So that gives you that pressure due to gas equal to pressure due to atmosphere. So in this case, pressure of the gas is 740. Torr is same as millimeter of mercury. That's the unit that we are going to use. Now here you're looking at a barometer. Now barometer is for outside pressure measurement. At the sea level, that would be 760 millimeter height of mercury. So you have a long tube, if you fill it with mercury, and if you take it at the sea level, what you are going to notice is mercury level would come down and it would stand at a distance of 760 millimeter from the surface of mercury. So that's H is 760 torr, or millimeter of mercury. If outside pressure is decreased, the mercury level would come down. So in other words, outside pressure is going to balance the height of mercury. And that's why height of mercury in barometer would indicate the outside pressure. And we're trying to explain that to you with seesaw analogy. So this is the height of mercury, and on the left hand side on the other side you have only atmospheric pressure. So they are balancing each other. Now let's go over a problem now from the book, which is problem number 25, page 416. In problem number 24, I'm going to do part 2 and part 3. Part 2 is on open-end manometer. So this is a basically manometer, and this side is open to atmosphere. In other words, on that end, we'd expect atmospheric pressure. And it is given, atmospheric pressure is given to be 0.995 atmosphere. Also, we know the difference in the height of mercury on the right side to left side is 67 centimeter. Now, question is, what is the pressure of the enclosed gas sample? Again, there are two ways you can do this problem. First, by looking at it, can you tell me whether pressure of the gas, let's write down that question, is pressure of the gas, oh, we have this question too at the bottom, greater than 0.995 outside pressure? Is it equal to 0.995 or less than 0.995? Just by looking at the mercury on the right hand side, you'd be able to answer it. In last example, we had pressure of the gas same as outside pressure, and we had the mercury level on both sides of the tube was the same. Now in this case, mercury level on right side, this side, has gone up. So that tells us that pressure of gas must be greater than 0.995 atmosphere. So once we know it is more than 0.995, by how much is more? By this height difference, which is 67 centimeter. So let's change it to millimeter. So pressure of the gas, I can readily write down, is given by 0.995 in atmosphere, and you're going to add 67 centimeter because the units don't match, so you'll have to, let me first write down in this way, and then we think about writing down in right unit. Now atmosphere needs to be changed to millimeter of mercury, if that's how you're going to express it. I think the question didn't ask us to express in a particular unit, so you have the freedom of either expressing the final unit in atmosphere or in millimeter of mercury. So I can do that in millimeter of mercury. Let's write down 0.995 atmosphere and multiply that by 760, that's torr or millimeter of mercury per 1 atmosphere. So that gives me in torr, and I'm going to add 67 centimeter times 10 because 10 millimeter makes a centimeter. So it's going to be 670. Millimeter of mercury is same as torr. So keep that in mind. So those two numbers are added would give you pressure of the gas. That's one way of doing it. The other way of doing it is basically by imagining a seesaw. Now I have drawn a dotted line. So on one side of the dotted line, let me show you that. Say, assume that this is the seesaw, remaining horizontal. On one side of the dotted line, I have a gas, pressure of the gas, and that's balancing the height of 67. Let's write down in millimeter, 670 millimeter plus 0.995. I think I'm running out of space here. So on right hand side, you have a total pressure of 670 is due to the height of the mercury plus 0.995 that has to be changed in millimeter of mercury. Basically, you need to add those two numbers and we get the same answer, no matter which way we do it. In part 3, you have closed end manometer. That means this end is closed. It's not exposed to atmosphere, and you have vacuum on the top, right underneath that. So the space that you see, this is vacuum. Okay, now in this case, let's again ask that same question. Of course, there is a vacuum, so there is no pressure on that open it on that side, other than the height of the mercury. So what is going to be the pressure of the gas? Well, pressure of the gas, if you think about seesaw, let's assume that this is the seesaw. It's sitting on it and it's a horizontal line. On right hand side you have 10.3 centimeter height of mercury and nothing else there. On left hand side you have gas. So pressure of the gas is equal to 10.3 centimeter. I can change it to millimeter of mercury because that's how millimeter of mercury is torr, 103 torr. So that's the answer to this question. Standard pressure is considered to be 1 atmospheric pressure, and that you'd expect at the sea level. And 1 atmospheric pressure would be same as 760 torr. That's the 760 millimeter height of mercury if you make a barometer with mercury. And in terms of Pascal, it would be 101.325 kilopascal. As I said, we are not going to use Pascal too often, but it's just mostly this unit, either millimeter of mercury or atmosphere. These are the two units we are going to use most commonly. Now we're going to discuss about different gas laws. Now Boyle's law for volume of a fixed quantity of a gas at constant temperature is inversely proportional to the pressure. Our common sense tells us the same thing. If you exert higher pressure, the volume is going to go down. So volume is inversely proportional to pressure. And these graphs indicate that too. Charles' law, the volume of a fixed amount of gas at constant pressure is proportional to absolute temperature. That means as you increase temperature, volume is going to increase. As you decrease temperature, it's going to decrease. And that's what you are seeing in this experiment. When you cool down a gas sample in a balloon, as you can see that balloon decreases the volume because you're lowering the temperature. Avogadro's law, the volume of a gas at constant temperature and pressure is proportional to the number of moles. That means if I have larger number of moles, there'll be larger volume. Smaller moles, there'll be smaller volume under same pressure. So now I'm writing down all these expressions. Volume inversely proportional to pressure is the Boyle's law. Volume directly proportional to temperature, that's Charles' law. Volume directly proportional to number of moles, that's Avogadro's law. When you combine them, you're going to get volume is proportional to NT over P. Now then you can write down proportionality. If you replace proportionality by equal sign, then there'll be a constant. So you'd have a constant times NT over P. And that constant in gas law we represent by R. So let's now write down as nRT over P. And this is considered to be ideal gas equation. And R has a fixed value which is 0.0821 liter atmosphere per degree Kelvin per mole. For an ideal gas, we already mentioned that you get PV equals to nRT, where N is number of moles of the gas, R is a constant, which is 0.0821 liter atmosphere per degree Kelvin per mole. Now, this expression that you are seeing can be used if one pressure is given, say one volume is given, and say you need to calculate temperature. So just solve for temperature. And I can show you that from here I can write down PV over T equals to nR, which is a constant for a fixed mole of gas. However, quite often we deal with two different pressure values. That means if I know a volume at a particular pressure, what could be the volume at a different pressure or a different temperature. So how do I do those kind of problems? You can derive this expression from PV by T equals to NR. Say I have different pressure units, P1 and P2, so I'm going to write down this expression as P1V over T1, P1V1 over T1. V1 is the initial volume, T1 is the initial temperature in Kelvin, must be equal to second pressure times second volume over second temperature. Again, temperatures are always in Kelvin. Now this is going to be true for a fixed amount of gas. Here you can see that number of moles is PV by T gives number of moles times the gas constant. So gas constant, again, I want to remind you this is 0.0821 liter atmosphere degree Kelvin mole. Now let's go over a problem. I think we're in next slide we discuss over a problem. Now the problem that I would like to go over is 10.28, and I'll go over B as an example. If you read this question, it says that a fixed quantity of gas, that means they're not changing the amount of the gas, that at 21 degrees centigrade. So initial temperature is given 21 degrees centigrade at a pressure of 752 torr and gives a volume of 5.12 liter. So these are all initial values. Calculate the volume of the gas, which is the final volume, if the temperature is increased to 175 degrees centigrade while the pressure is held constant. So pressure is remaining constant, but we still have two different volume and two different temperature. So obviously we need to use the expression that I just mentioned, P1, let's write down here, P1V1 over T1 equals to P2V2 over T2. Now we know in this case pressure 1 is equals to pressure 2. So I can now cancel out those pressure 1 and pressure 2. So I'd be left with volume values. Okay, now let's write down what information we have. Temperature 1, they have given 21 degrees centigrade. Remember, your temperature will have to be in Kelvin. So add 273, and this gives 294 Kelvin. So that's temperature 1. Even though they gave you the pressure value, you don't need it because pressure is kept constant. The volume 1 is 5.12 liter. You need to calculate volume 2 at a different temperature. So temperature has been increased to 175 degrees centigrade, and you add 273 to that, and that gives you 448 Kelvin. So when temperature is increased to 448 Kelvin, what would be the new volume? Okay, so let's now use that expression that I have given on the top and solve for volume 2. So when you're solving for volume 2, let me do that. So volume 2 would be given by volume 1 by temperature 1 times temperature 2. This is a simple algebra coming from here, so I hope you could be able to do it. Now you can just plug in numbers, because we know that volume 1, 5.12 liter, 5.12 liter, it's good to write down units. Temperature 1 is 294 Kelvin, 294 Kelvin, and temperature 2 is 448 Kelvin. 448 Kelvin. Now we can cancel out. Kelvin would cancel out. And my final unit would be liter, and that checks out because this is volume, and that value is 7.80 liter. So this is the answer to this question.